Okay. Welcome to another session in control system, and today we are going to look at the signal flow graphs. From our previous tutorial, we looked at the block diagrams, and signal flow graphs are just related to the block diagrams. And you'll find that in most cases, the most extensively used graphical representation of a feedback control system is always the block diagrams. But at times you find that the block diagrams that we are talking about here are very complicated. They consist of several pick-off points and several summing points, and this one makes them to be tedious in case we are using the block diagram reduction rules that we talked about earlier in block diagrams. So in this case, the alternative approach is always to use what we refer to as the signal flow graphs. And under the signal flow graphs, you'll find that in this alternate approach of the signal flow graph, by a technique, we usually use a technique that was developed by somebody called S.J. Mason, whereby we use this, what we'll talk about later on as the Mason's gain formula, in order to come up with the transfer function. So this one is a little bit easier as opposed to getting the transfer function of a system, especially if it is very, very complicated. And that one can make it to be very tedious. And so we will use the signal flow graph in order to determine its transfer function. So basically, when you talk about the signal flow graphs, these ones are just pictorial representation of simultaneous equations that describe a system. So in this case, they usually graphically represent the transmission signals, and we can consider a simple equation whereby we can talk of two nodes, whereby one of them is the input and one of them is the output. So we can say that we have this one. The input can be xj. We can talk of this one to be xj, and then this one is xi. So that we have a node here. So this one is a node, and this one is also another node. And then in between, we usually have what we usually call the transmittance or the transmission function. And we usually name it, like in this case, we can name it as A. And then we start with the one for the output node, I, J, whereby Aij is what we call the transmittance or the transmission function. So this one represents an equation whereby we can say that Xi, which is the output, is given by Aij times Xj, whereby Aij is the transmittance or the transmission function, and A is actually the gain. Ij shows the direction, whereby we start with that I, which is at the output, and then J, which is at the input. And therefore, this particular signal flow graph, the simple signal flow graph that we have here, is actually showing this. It can be represented by this particular equation. So that is basically what a signal flow graph is. And we can see that the signal flow graph has got node. It has got a transmittance, so which is the gain. Transmission function or the transmittance, which is the gain. And this one is between each. It has to exist in every branch. So I want us to look at the signal flow graph algebra. So we can look at signal flow graph algebra. Signal flow graph algebra. So when you talk about signal flow graph algebra, we are going to look at the three rules that are always used in signal flow graph. The first one, we are going to look at the first rule that we are going to look at, and that is what we shall refer to as the additional rule. Additional rule. The additional rule. And when you talk of the additional rule, then we can talk of that. We can have that. Let's say that is a node. So those ones are the nodes. Then from these nodes, we have, we can talk of this one to be x. We can talk of this one to be x1, x2. Then maybe there are several nodes in between. Then there we have xn, whereby when we have the additional rule, then here we can talk of that, the nodes moving in that direction, so that we have the additional, so we can have this one as our xi. Therefore, if we name it the same way, then it means that we are going to have a1i, or we have we can have that. Then from there, we know that if we talk of this, then we can talk of our xi here will be the summation or the sigma of this from n, and where we can talk of j is equals to 1, and ai xj. ai xj, which means if we want to get what this xi is, then it means that we are going to get x1 ai, x2 ai, plus x3 ai until we get to the xn ai. So this signal is actually the summation of all this. This is actually the summation of all these. So I think the direction is not right. So we can have them converging. They are supposed to converge. So that is what we call the summation or the additional rule, whereby they are all the signals are coming to xi. So the sum of what is happening at xi will be this one times that one plus this one times that one plus all that are in between until you get to xn in order to get to xi. So this is what we call the additional rule. So the additional rule is always very, very important. So we usually say that under the additional rule, we say that the value of the variable that is designated by the node equals the sum of all the signals entering the node. And the equation is given by this. So that is what we refer to as the additional rule. So we want to go to the next rule. That is the transmission rule. Transmission rule. Can go to transmission rule. Transmission rule. So that is the second rule. Transmission rule. So when you talk about the transmission rule, then in this case, it is almost, it is more or less the same as what we had before, but now instead of converging, it now diverges. So we can have something like that. Maybe we can talk of something like xj, then xj is there, then you have that, then you have that, then you have a node here, we have a node here, then it is now they are living in that direction. So now they are, then we can have x1, x2, can have x1, x2, then xn. So they can assume that there are several in between. Then here we can have a1j, because it is going to that, a1j, a2j, anj. So we have all that. So that is how it is supposed to do. So how it's supposed to be. When you talk of the transmission rule, then when you talk about this rule, then it means that the value of the variable that is designated by the node is transmitted in every branch, and therefore, in this case, the equation can be given by x1 here, or xj. We can talk of xj to be consistent. Is going to be given by, xj will be given by x1 here, or it will be given by x1. So we can talk of, it will be given by, we can start with the transmission function, a1j x1 plus, that is what we are going to find. We can generalize this, whereby because it is I that is going to change, whereby we can talk of I, we can talk of having I to be equals to any integer where I can be any integer until you get to n. And so that is what we have, and it can be represented by this. So what we mean is that this xj will always be in every transmission, the xi will always be in every transmission function. Therefore, it is that signal that is leaving that particular branch. So in this case, we should know that where j is fixed. So that is what we refer to as the transmission rule. Then we can talk about the third rule, which is now what we refer to as the multiplication rule. We can talk about the multiplication rule. 3, we can talk about multiplication rule. We can talk about the multiplication rule. And when you talk about the multiplication rule, then what we simply means is that in any series or cascade connection of branches that have got transmittances, let's say A21, A31, A32, and the rest, can always be replaced by a single branch with a new transmittance that is equal to the product of the individual transmittances. So that is to say that if we have maybe a system like that has got several, can talk of x1, can talk of x2, can talk of x3, can talk of maybe x4 until we get to maybe xn. So if we have a system that has that, then of course, by naming that, we can talk of this one as A21, A32, A43, and so on, so that we can have up to that. So if we have a signal flow that is represented by that, then this one we can reduce it by simply having two branches. So that two nodes, like we can talk of x1 to be there, then the last one, which is xn, and then in between here we have the products of the various transmittances, whereby you can talk of A21 times A32 times A43 and so on until you get to xn. So that is what we refer to as the multiplication rule, whereby a series or cascade connection of branches with the transmittances A21, A32, A43, and so on can be replaced by a single branch with a new transmittance that is equal to their product or the product of the individual transmittances. And that is how that one can be represented. Or you can still say that xn in this case can be given by we can multiply x1 into we can talk of A21 dot A32 dot A43 and so on, and that is now what xn is all about. So that is what we refer to as the multiplication rule. So all these three rules, we'll be using them in order to help us obtain the transfer function of a system by use of the signal flow graph. So those are the rules. So before we can get to obtaining the transfer function, it is very, very important that we know some of the definitions. So we are going to look at the definitions in signal flow graphs. We're going to look at the definition in signal flow graphs so that we can get to the Mason's-Gain formula and be able to get the transfer function of various systems. So let's look at definitions in signal flow graphs. Definitions in signal flow graphs. Definitions in signal flow graphs. And for us to get more about the definitions in signal flow graphs, maybe we can have a drawing, a small drawing here. So we can have that. So this one is x1, x2, x3, x4, x5, x6. Then we can have this one to be A21, A32, A43. Then here we can also have A54 and A65. So that one can be, we can have at x3 here, we can have something like that. Maybe we can call this one A33. So we are going to maybe making reference to this when we will be carrying out our definitions. So we can have that. We can have it from x3 to x2 here. So that this one will be A23. Another one we can have between x2 and x4. So this one can come to that. So that here we have it moving forward so that we have A43. So we can have A43 there. Maybe we can have between x4 and x5 here. So that we have that. So that it's A45. So maybe we are going to make reference to this when we'll be carrying out the definitions. So under this, we are going to start by defining what a node is. So we can start with a node. A node. So a node is, in this case, when we talk about the signal flow graphs, we usually represent the signals in terms of nodes. And therefore, a node is just a system variable that equals the sum of all incoming signals. So, like in that case, we have the node x1, x2, x3, x4, x5, and x6. All these represent the nodes. And these nodes are usually represented by a small dot. So, we have them represented by a small dot. So, nodes are just showing the variables, and they can be defined as a system variable that equals the sum of all incoming signals. And as such, we can talk of x1, x2, x3, x4, and x5 as the nodes of that particular system. And in fact, just to summarize, nodes are simply variables that are used in a system. So whenever there is a change in a variable, there will be a node. The second one that we can talk about is the branch. Branch. So when you talk about a branch, then you'll find that when a signal usually move from one node to another. So signal usually move from one node to another. That particular movement from one node to another, that line, like where we have the A21, the A32, and so on, that is what now we usually refer to as a branch. So the movement from one node to another is what we usually refer to as a branch. That distance between one node and another is what we refer to as branch. Therefore, you can say that a branch is always where the signal travels from. So we find that a signal travels along a branch from one node to another in the direction that is indicated by the branch arrow. And this signal is always multiplied by the transmittance or the transmission function of that particular branch. Like, for example, we've talked about the branch of x1, the branch between x1 and x2, multiplied by the transmittance of A21, the branch between x2 and x3, multiplied by the transmittance of A3, A2. And therefore, that line that connects two nodes is what we usually refer to as a branch. The third one, we can talk of what we refer to as a path. We can talk of a path. So a path is basically a unidirectional succession of branches along which no node is traversed more than once. So a path, basically a path can be a branch or more than one branch. So, and you don't need to repeat a node twice. The node has to be traversed once. That is what a path is. That is why we refer to as a path as a continuous unidirectional succession of branches along which no node is traversed more than once. Like we can talk of x1 to x2 can be considered a path. In fact, x1 to x2 can be considered both a branch and a path. Then we have x2 to x3 can also be a path, but we can also talk of a path x1 to x2 to x3. But now it has got 2 branches. It simply means that you don't need to traverse a node more than once for you to have a path. We can also talk of the whole x1 to x2 to x3 to x4 to x5 to x6 as a path, because basically we are talking of several nodes, but we are only traversing these nodes once. The next one that we can talk about in number 4 here is what we refer to as the input node or the source node. Input node, or what we shall refer to as the source node. The input node or the source node. So basically when you talk about the input node or the source node, then this is the node with only outgoing branches. It should not have any incoming branches. So if you look at from our diagram, if you look at the signal flow graph that is on the board, then you'll find that what will be representing the input node is x1. Because x1, if you look at x1, it only has outgoing signal, which is going to x2. It doesn't have incoming signal, and therefore we can refer to that as the input or the sink node. Like we can refer to it as the input or the source node, and that is in this case the input node in this case is x1 because it only has an outgoing branch. The next one that we can talk about now is what we refer to as the output stroke sink node. Output stroke sink node. Then this is node with only incoming branches. In this case, we are only talking of a node that has got incoming branches, and we can talk of x6. An example of this is x6. So x6, if you look at it, it only has one branch that is coming to it, and the branch is coming from x5, and therefore that is what we refer to as the output or the sink node. So as we have said, the output or the sink node is simply a node with only incoming branches. Now we can look at number 6, which is now what we refer to as forward path. So we've talked of path. So now we are talking of the forward path. The forward path will be very, very important in determining the transfer function using this method, and therefore it is very, very important for us to identify what a forward path is. So a forward path is that it is a path that comes from the input node. It must come from the input node to the output node. So like in this case, whenever it still has the definition of a path, whereby we are not supposed to traverse a node more than once. So when you talk of the forward path, then it means that it must come from x1 and it must end at x2 without traversing a path more than once. Like in this case, we can talk of x1, like one of the forward paths can be x1 to x2 to x3 to x4 to x5 to x6 can be considered to be a forward path, or we can also have x1 to x2, then moving up there to x4 to x5 to x6 can also be a forward path. And therefore, when you talk of the forward path, then it must come from the input node to the output node, and just like from the definition of the path, it must not traverse a node more than once for it to be considered to be a path. Then we can talk about number 7. We can talk of the feedback loop. We can talk of the feedback loop. The feedback loop. So when you talk about the feedback loop, then this is a path that originates and terminates on the same node. It has to originate and terminate on the same node. So like in this case, you can talk about this. You can talk of x2 to x3 and back to x2. Remember, you don't need to change the direction of any arrow for you to consider it to be a path. So we have to be a feedback. Like we cannot talk of this one to be a feedback because it is moving forward. So it must have one of the branches moving in the feeding back into the where it started. Like we can talk of x2 to x3 to x4 as a feedback loop. We can still also talk about x4 to x5 and back to x4 as a feedback loop. But we are not going to talk about this, even though it is a feedback loop, but it is a special feedback loop that we are going to define in our next phase, which is self loop. So number 8, we are going to talk about a self loop, and self loop is basically a loop that consists of only one branch. So this is a loop that consists of only one branch. Like in this case, we are talking about a loop that goes from the same node and returns to the same node without getting into any other node. So in that case, we are talking about this as the self loop. In this case, we can talk of A33. Like a good example is A33 can be considered to be a self loop. Number 9 here, we can talk about what we refer to as a gain. Gain. So when you talk about the gain of the branch is simply the transmittance of that particular branch, and where, in this case, where the transmittance or the transmission function is a multiplicative operator. For example, we can have A33 to be a gain. We can have A21 to be a gain. We have A32 to be a gain. We have A43 to be a gain of those particular respective branches that are there. So when you talk about the gain, then we are simply talking about the transmittance of that branch, where the transmittance is a multiplicative operator. And in that case, that is what a gain is. Then number 10, we can talk about what we call non-touching loops, going to be very important in determining the transfer function. So we can talk of non-touching loops. So when you talk about the non-touching loops, these ones are simply loops that do not share a common node. So if we have a loop that do not share a common node, then they can be said to be non-touching. Like in this case, we have this loop, a loop x2 to x3 and back to x2, and the loop x4 to x5 and back to x4. These loops, we can refer to them as non-touching loops, because looking at them, this loop is x1, it's x2 to x3 and back to x2. And the other one is x4 to x5 and back to x4. So if we look at this loop, they don't share any common node, and therefore we can refer to them as non-touching loops. But looking at this and self loop, you can see that there is the common node. This node is common to this loop and that loop, and therefore we cannot refer to them as non-touching loops. So that is the definition of non-touching loop. So we've said that non-touching loops, we are just loops that do not share a common node, and that is what we refer to as non-touching loops. The next one, we can talk about the path gain. Path gain. So when you talk about the path gain, then this is just the product of the branch gains that are encountered while traversing a path. So we are talking about the product of the transmittances. Like for example, when you talk about the path x1, like we can talk of x1 to x2 to x3 to x4 to x5 and finally to x6. So that one is a path, and if we talk about that, then we can talk about its path gain. We will have a path gain of A21. We will have a path gain of A21, A32, A43, A54, and A65. So that is what we refer to as the path gain. So it is simply, the path gain is simply the product of the branch gains that is encountered while traversing a path. And the example, you can talk of x1 to x2 to x3 to x4 to x5 has a gain, has a path gain that is given by A21 times A32 times A43 times A54 times A65 and so on. Then we can also have what we refer to as in number 12, we can talk about loop gain. Loop gain. So when you talk about the loop gain in this case, then the loop gain is just the product of the branch gains of the loop. Just the product of the branch gain of the loop. Like in this case, the product of the branch gain of the loop. Like in this case, we can talk of the loop x2 to x3 and back to x2 as having a32, as the loop gain will be a32. Can talk of a32 times a23. So that is the loop gain for that. When you talk about this, x4 to x5 and back to x4 has got a loop gain of a54 and a45. The product of the two will give us what we refer to as a loop gain. So those are some of the definitions that are very, very important for us to understand before we can get to get to the Mason's gain formula in order to use the signal flow graphs so as to obtain the transfer function, as we had said earlier, that this is just a way of obtaining the transfer function, just like the same way we use the block diagram reduction rules. But now, because some block diagram reduction, some block diagrams may be complicated, we can always use this in order to obtain the transfer function.